So welcome everybody. This is the second lesson or second session of our exercises in Mathematics 1. We have a new topic today. I wanted to show this first actually. Our new topic is, as you know, complex numbers. There will be plenty to do about complex numbers today, but we have two little items left from last week. One is once again back to these logic proofs where I made the experiment, you could say, by a lack of time, to do this proof just in words. And I remember that I made a little mistake when describing the situation. So let's try again just for case 3. What's important about this whole big implication? So the essential point is this, that something complicated implies R, simply R. That's what we want to prove. So if we talk about premises and conclusions, we find that the conclusion is simple, it's just R, logical variable, but the premise, and I may say the total premise of this implication is a compound expression by an AND operation between 3 different, constituents. So, and in the positive case, I think that my argument was correct when I said we need that the total premise is sufficient for the total conclusion. I say total because so that you don't mix it up with the, these little implications inside, because they have their own premise and their own conclusion, where in this case the conclusion is the same as the total conclusion. But I will say total so that you can understand what I mean. So let's look. To show that the total premise is really sufficient for the total conclusion means that we look what happens if the total premise gets true. What do we need for the premise to be true? And then this is what I wrote here in blue color, but I say it again. For this to be true, we must have a valid implication here, so that it has a truth value of 1, logical 1, which means that inside here, the little premise Q is sufficient for conclusion R, and also here, so that this gets true, this little premise P must be sufficient for R. And that's why I wrote P is sufficient for R and Q is sufficient for R. Both is independent from each other, which means it would be actually sufficient if P alone or Q alone are true, so that R gets true. And now, nicely, we have the additional requirement that P or Q is true, so that the whole total premise gets true. Also, this term must be true, which means that at least one of P or Q is true, so that also at least one of these premises actively guarantees that the conclusion R gets true. And that's why if the total premise is true, we have a guarantee that also the conclusion R gets true. So I think now this was a little more to the point this time. So I showed that in this whole big implication, the total premise is sufficient for the conclusion. Now I wanted, last time, I wanted just by, for security or for safety, I wanted to check also the other point, which is called that the conclusion must be, how did we say? The conclusion must be what? Not sufficient, but necessary. Yeah. So again, premise is sufficient for the conclusion, but the conclusion should also be necessary for the premise. What does this mean now? It means that I must also check whether, and then it's interesting to take the negative case. That's what I was trying to do. What happens if the conclusion is false? And if we then find that anyway the total premise could be true, then we would be discovering the contradiction case, which we don't want. You remember the contradiction case of an implication is always that the premise, the total premise, is true, but the conclusion is false. So that's another way of checking it, and that's what I was trying to do, and there I made a certain mistake. So I try again. So now this time I suppose that the conclusion is false. So I have a logical 0 here, and then I check what this means for the truth value of the total premise. So this time R is logical 0, okay, here and also here. Now, on the other hand, if the conclusion here is false, you know that this means that this time the little, if I may say, the little premise must not be true, because now if Q were true, I had 1 implies 0, which is false. And okay, on the other hand, it might be, well, it might well be, but in that case, I would have a logical 0 here already, which is fine. But on the other hand, since there's an and here and an and here, in this case, if now R is false, which we suppose, and Q would be true, then the whole and, the double and combination or operation would fail. So I would have a logical 0 for the premise, and that's fine, because that means if R is 0, also the total premise gets 0, and we have no conflict. Yeah, we just have a conflict if this suddenly gets true, although the other hand side, the conclusion side is false. You remember, I'm always spotting the contradiction case, no? the critical case. So that's okay. But on the other hand, if Q is 0 now, then this is fine. 0 implies 0, so then this would get true. Now we would have to check all the different cases, but and let's suppose Q is 0 and P is also 0. So both implications here are still valid, although the right hand side is 0. Yeah, you know that 0, 0 is a clean row in the implication table, truth table. So we would have actually a logical 1 here and a logical 1 here, but only if Q and P are both false. So this means inside here that the OR gets false. Neither P nor Q are true in this case, so this gets a logical 0, and then actually I have something like 0 and 1, which is still 0. And there was my mistake. Last time I was telling something about 0 and 0 and 0, which it's not. And it can be 0 here, it can be 0 here, but in that case, either Q or P are 1, logical 1, and then the OR gets true. But anyway, still, even then, the whole thing gets false. So a little complicated it was, but in the end, I've shown that if the conclusion gets false, it enforces also the premise to be false. So we never will observe. We never will observe the critical case where the total premise is true, but the conclusion is false. This is still an oral proof, not more and not less than that. But I just wanted to fix this. Okay, so anyway, time is running, so I make a jump to our homework, which is this one about maps. No, this is the next one. Sorry, here, this is also a little mistake because we have exercise 1.6, we have it twice. This should be 7, of course. Perhaps you noted this. Okay, so it's 1.7 about maps. Now, again, it's a little, I don't know, it's a little hard to make a purely mathematical solution by just using standard formulae or standard equations. So I tried just to explain it in words and by inspection. So let's just make clear what we have. In case 1, which says that natural numbers are mapped to natural numbers, So about the terms a little bit, we know this is called, the left side is called the domain, also with a capital D, and the right-hand side is called the codomain with capital C. And there is a certain distinction between the so-called codomain and the so-called image, as you know, because the image denotes those values of the dependent variable, mostly y in our notation, those values which are actually reached by using the function. So you could say the codomain denotes the values of y which are allowed, and the image, a little more exactly, denotes those values of y which are actually observed by using this function. So you'll see the difference right now, okay? So I examined just several sources and images of this first map. Let's just use our natural numbers for n in ascending order. I start out with 0. That's our convention. That's the 0 is included as last time. And so I say, okay, what happens if I put in 0 here for n? Then I have 0 plus 2 is 2, of course. 2 squared is 4, so that's easy. Okay. And also the next one, 1. 1 plus 2 is 3. 3 squared is 9. And it goes on with squared numbers. Okay. The 2 is mapped to 16, the 3 to 25, and you can easily guess how the whole thing is continued. So what we see is of the well-known squared numbers in the domain of squared natural numbers, the only one missing seems to be 1. That has to do with the domain restriction. Also 0 is missing on the right-hand side, so but that's no problem. We have another problem. It's quite obvious, and that's why I just write it down here. It's obvious that this map is strictly monotonously ascending. That's not a problem now. That's you could say that's a positive aspect. Why is this important? Why is monotony important at all for our questions here? And the reason is that a map to be injective requires it to be monotonous. I don't know if that was proved or something in the script, but you can easily find out by yourself, because you know what it means to be injective for a map. It means that if you try to go the way back from your dependent calculated value to the independent variable's value, okay, so you just like you try to turn the arrow around and to go back from 25 to 3 where it came from. If you do this and you do not get a unique result, then you have a problem with injectivity. So a map is only then injective if the way back from y to x is, how do you say, is clearly a one-way calculation.
It is unique.
Yes, it's unique, right? And we see by monotony, we have a guarantee that this is the case. So this map is obviously injective. Also, a good formulation is this. It means that at most one x is there or exists for, yeah, it's just a little, not really a strict notation here, for all y element codomain. So for all allowed values of y, we find at most one value of x, not 2 or 3 or even more. So that's the point. Now, on the other hand, but it's also obvious that all the images are squared numbers, squared natural numbers greater or equal to 0. Greater or equal than 4. So now about the so-called image. The image denotes those values of y which are really reached by using the function. And this notation is not very perfect either. I just tried. I write down this way: y element, of course, element n. Then it holds that y is greater or equal than 4, because that's the lowest one we find anyway. Then also y is some, this should just say it's some squared natural number, okay? And this holds for all n greater or equal than 2, because 2 squared is 4. And anyway, so what I want to say is the image contains only squared numbers, while the codomain contains all the natural numbers. And we all know that many of the natural numbers are not squared numbers. And that's all. We can say there exists at least one value y, so that y is element of the codomain and is not element of the image. So that means our map is not surjective. That's all surjectivity is about. It's about the question: do I have at least one value of x if I present any valid value of y? That's the way you do it. Yeah, you say I pick just a valid number for y out of the codomain, and then I check if there's a matching value of x, so that I can, you could say that I can construct the inverse map. Yeah? It's all about the inverse map, the existence of the inverse map. So here we made sure there is at most one x for all the y's. And here we find out there is not at least one x for all values of y. Just an example, if y is equal to 17. 17 is not a squared number, so we don't even, look here, we don't even manage to draw the root, and then we would have to subtract 2 to find our value for x. But the first step is to draw the root, and this is in this domain, this is just not possible. So that's, I think that's not hard. I just try to explain it in detail this time only, and never again. So after all, this map is not surjective. It is injective, but not surjective, and that means in the end it's not bijective. We all know that bijectivity means that our map would have to be as well injective as surjective. These both attributes must hold, and if you take them together, you call what you get, you call it bijective. And this is also directly relatively easy to understand what it means. It means that you have a map which is in both directions unique in both directions. That's what bijective means. And okay, clearly this demands these two very different aspects, as we call them, injectivity and surjectivity. Now, in case 2, on first side, it's exactly the same. It's the same map, but this time the domain is the whole numbers. That means we also have negative numbers in the play or in the game. And of course, that's a problem, because squaring a negative number removes the sign, and suddenly we get, for almost every value of x, we get, no, sorry, I wanted to say, for almost any result in this map, we have 2 different sources on this side. I don't have, yeah, we can construct an example. I would say that if the contents of these parentheses gets positive 2, then the 2 squared is 4. That means that also n would be equal to 2. If I want to get negative 2 here inside, then I see, and I would have to take negative 4 for n. You see what I mean? And then I have minus 4 plus 2 is minus 2, squared is 4 again. So minus 4 and 2, these two numbers, minus 4 and 2, used for the independent variable x, would both map to the same value of on the image side. So that's clear. Okay. So in short words, it means in case 2 it's similar to case 1, but the domain is the whole numbers, whole integers. So this is not even injective. It's still not surjective, and it's anyway it's not bijective, but it's neither nor. Yeah. Okay. So the third one is like a little bit fun, if you want. Some of you may know this magical number 42, famously used by Douglas Adams in the Hitchhiker's Guide, and so it's become a very famous number in some respect. I don't know if it's right, but there's this a rumor which says that Douglas Adams, the book author, if you know him, he's died sadly many years ago. The idea for this number came from the so-called rainbow angle, because it's the angle under which you can see a rainbow, quite exactly 42 degrees by chance, which has to do with the anti-solar point, and it's a caustic phenomenon, right? Surprisingly complicated phenomenon behind the rainbow, but it also took a long time to find out what's really happening there, by the way. So, time, looking at my clock. What's happening here? Well, it's a good idea to, here we have n to n again. It's a good idea to start with this special case, because it's just valid for n equals 0. So that's what I did. I examined the mapping again, and then we quickly find that the first source we take is 0, then in this case we get 42 as an image. So then all the other natural numbers beginning from 1, ascending 1, 2, 3, etc., are mapped to their how do you say, their predecessor number. Yeah, so the number that is lower 1, yes, that's just preceding them. So you subtract 1. So that means 1 is mapped to 0, 2 is mapped to 1, 3 is mapped to 2. And now don't forget to go on in your mind and then find that 43 is this way mapped to 42. That's the problem. Due to this rule, we get the same result as in the case x, if I may say x equals 0. Yeah. So that means it's just one special case, but it's there, and because it's there, this function is suddenly not bijective, which means if I choose by chance, if I choose the 42 for my image value and try to calculate back the yes, you know, the according source value, I will find two different results, like 0 or 43, and this is a clear conflict with the attribute of injectivity. So it's just one example, and just in this case it takes place, but if it takes place even only once, it means that the mapping is not injective. It is surjective. It's surjective, that's without explanation. I think you all know. You can see it here. Here we get, as an image, we get the rising series of, in ascending order, the series of natural numbers, 0, 1, 2, 3, and so on. There's no limit. So we get them all, and that means that the image is equal to the codomain. So that's fine, but injectivity is injured, which again means that the whole thing is not bijective. So in all the three cases, we don't have a bijective map. Fine, did you get something similar? I hope so. So then it's time for complex numbers soon.